Good day. We're looking at part 1 of limits. Looking at part 1 of limits. So this is basically the introduction. So introduction of limits. So this is the introduction of limits. Okay. So when you talk about the word limits, what does it mean? So the word limit can also refer to limits can also refer to the furthest point. The word furthest point. Now in our particular lesson, we are going to look at concepts about limits. Concepts about limits. Now the idea about limits is we take a value that is closer to another word specific value. So let's take this function. Let's say f of x. Let's say f of x is equal to x plus 2. So we are taking f of x is equal to x plus 2. Now let's take the range, a certain range of values. So let's take 1, 2, 3, 4, and 5. Right? Okay. Now we are saying that we are going to substitute each of these values into what? This x plus 2. So f of 1 will be equal to 3, f of 2, 4, f of 3, 5, f of 4, 6, and f of 5, 7. F of 5, 7. Now you can see that as we approach the 5, you can see that as we approach the 5, all these values tend towards approach to this 7. So as we move from 1 into 5, you can see that these values here, so 3 also approaches 7. 3 also approaches 7. So we are seeing that when evaluating limits, we are looking at a certain value from a point, giving us another value from a different point, whereby these values are close. So you can see 3, so 1, 1, 3, they are increasing, and they are all these numbers are getting close. So let's say if we want to take 5, rather 5, you can see that 5 has 7. The value of 5 is 7. Now you can see that from 1, 2, 3, 4, as it took their values as 3, 4, 5, and 6, all these values approach the 7. All these values approach the 7. So you can see. So if you're asked to write a limit, so limits are written as, so you write so this is said as limit as x approaches a of f of x equals L, or is equal to L. So limits as x approaches what? So this limit as x approaches a of this f of x is equal to L. Is equal to what? L. So we are saying that if you look at this particular example, let's say our f of x is s plus 2. Now, as x approaches a, let's take our interval from 3 to 5. Now, as 3 approaches 5. As 3 approaches 5. Then the values of now 5 and 6 are actually close to 7. 5 and 6 are actually close to 7. Now you can see the difference between 5 and 7 is what? The difference between them now, 7 minus 5 is 2. The difference between 7 and 6 is 1. 7 and 6 is 1. Now you can see as the x approaches a, the values are increasing. The values are increasing. Okay. So we are seeing that we can actually make the values of f of x close to L by taking x to be sufficiently close to a. sufficiently close to what? A. So let's take our L to be 7. Let's take our L to be what? 7. Right? Let's take our L to be what? 7. Then let's take our X to be 3. Now we are moving from 3 to what? 5, right? 3 to what? 5. Now we know that that's for 3 is what? 5, and that's for 5 is what? 7. Now you can see that as we move, so 5, 7. As we move from 3 to 5, the values are what? Close to each other. 5 to what? 7. 5 to what? 7. Now, if you are asked to evaluate a limit, so if you are asked to evaluate limit as x approaches a of f of x, this will be f of a. So you substitute the what? The a into what? The f of x. The a into the what? The f of x. So it will be f of what? A. So let's take our x plus 2 to be our f of x. So f of x equals x plus 2. So the limit as x approaches 3 of x plus 2 would simply be 3 plus 2. 3 plus 2, which is 5. So the limit as x approaches 3 of x plus 2 will be 3 plus 2, and 3 plus 2, which is equal to 5. This is equal to 5. Okay. Now, in limits, we have left hand limits. So the left hand limits and the right hand limits. Left hand limits and right hand limits. Now, we are now looking at the left hand limit. So we want to look at the left hand limit. Now we are saying that for this left hand limit, if the values of a function, if the values of a function, if the values of a function at a point near to a so the values of a function at a point near to a tends to be a definite unique number. So tends to be a unique number. So the values of a function at a point a tends to be a definite unique number. Now the values of this function at a point near to a lies at the left of a. That's why it's left hand limit. So lies at the left of a. That's why it tends to be what? The left hand limit. So these values lie to the left of what? A. Now when you take a number line, the values to the left are all what? Negative, and the values to the right are all what? Positive. So right, left. So left are negative, right are what? Positive. So we are saying that this unique number is called the left hand limit of f of x at x equals a. So this unique number is called the left hand limit of f of x at x equals a. So this unique number is called the left hand limit of f of x at x equals a. Okay, now this is how it is represented. So we take f of a minus 0 is equal to limit as x approaches a to the power negative of f of x, which is equal to limit as h approaches 0 plus of a minus h of a minus h of a minus h. Now, so we are saying that we know that a minus 0 is the same as what? A. But because we wanted to compare this to the last one here. Now, this is how it's represented. So this is the actual way the left hand limit is represented. So values close to a by the left hand of what? A. So this a to the power negative is the same as negative a. So this is the same as what? Negative of what? A. This is the same as what? Negative of what? A. So it's the same as negative of A. So we are saying that if we take values close to the left hand of A, we are going to get what? F into bracket A minus 0. So that's F of what? A. Now if we take a limit as h approaches 0, positive of 0, which is 0 itself, we are going to get what? Limit as we are going to get what? Simply A. Simply what? A, because 0 will be A. So limits as h approaches 0 of plus A minus h. Now, so the same thing implies for the what? Right hand limits. So for our right hand limit, we have f of A plus 0 is equal to limit as x approaches positive A of f of x, which is equal to limit as h approaches positive 0 of f of A plus h. Now you can see that both of them are what? Plus. Both of them are what? Plus. Both of them are what? Plus. Sorry, this one was f. Sorry, f of A minus h. Sorry, f of A minus h. F of A minus h. As I said, it's being compared to the one here. It's being what? Compared to the one what's here. So if we evaluate this one to be 0, so we simply get what? F of what? A minus what? 0. Now here, so we simply get what? F of what? A plus what? 0. Now this is how it's represented. So limit as x approaches positive A. So the positive values of A which are close to A. That's what it means. That's why it's called the right hand limit. The right what? Hand limit. So right hand limits. That's why it's called the right hand limit, because the values of A are close. There are values of A which are close to A but lie as the what? The right hand of what? A. So right hand limits. Okay, then now we are saying that for a limit to exist, this is very important. For a limit to exist, we are saying the right hand limit must be equal to the left hand limit. So for limit to exist, right hand limit must be equal to the left hand limit. So the right hand limit must be equal to what? The left hand limit. Now I told you this is the actual way of writing it. So we have limit as x approaches positive of the A of f of x is equal to limit as s approaches negative of the A of f of x Okay, so now we are going to look at some basic things about how to evaluate limits. So basic things to know in limits. Okay, so the first thing we are going to look at is the multiplication of limits. Now we are taking two functions, so that is f of x and what? G of what? X. Now the limit as x approaches A, of f of x times g of x is equal to the limit as x approaches A of f of x times the limits as x approaches A of g of x. So these two are what? Equal. And the next one we take what? For division. So with the same f of x and what? G of x. So we are saying limit as x approaches A of f of x over g of x is equal to limit as x approaches A of f of x over limit as x approaches A of g of x, where g of x is not equal to 0. It's not equal to what? 0. But as soon as it's equal to 0, to make this one undefined. Now the third one is addition. So we are saying limit as x approaches A of f of x plus g of x is equal to limits as x approaches a of f of x plus limits as x approaches a of g of x. Now we go to the subtraction. We move to what? Subtraction. So subtraction, limit as x approaches a, limit as x approaches a of f of x minus g of x is equal to limit as x approaches a of f of x minus limit as x approaches a of g of x, of g of x. Okay, so these are basically four basic things you're supposed to what? Know. These are four basic things you're supposed to know. But I'm going to add a few. So we're going to dive into exponentials. We are going to dive into composites. We are going to also dive into trig forms. So the fifth one. So we are seeing limit as x approaches a of f of x, where this f of x is raised to g of x, can be written as limit as x approaches a of f of x into brackets raised to an exponent of limit as x approaches a of g of what? X. Of g of what? X. Then the sixth one, we are saying for the composite function, limit as x approaches a of g of f or in x is the same as limit of, so limits, then put the g outside. You know that g of f of x means g into brackets f of x, so we want to blend it in that way. So g into brackets f of x as x approaches a, and this is equal to g multiplying the limit as x approaches a of f of x, Okay, now let's move to the seventh one. So we are saying, this one is about log, this one is about logarithm. So we are saying limit as x approaches a of the log of f of x, is equal to log as x approaches a of f of x, so it's equal to log as x approaches a, so it's equal to limit as what? X approaches a of f of x, so the log of limit as x approaches what? A of what? F of x, where f of x is greater than 0. So note, f of x must be what? Greater than what? 0, because logs don't rate as negative numbers. You can't have log negative 1. So where f of x is greater than what? 0. Greater than what? 0. Okay. Then we look at the next part. We are saying, so 8, limit as x approaches a of f of x is equal to positive infinity or negative infinity. So if limit as x approaches a of f of x is equal to positive infinity or negative infinity, then the limit of 1 over as x approaches a of f of x is equal to 0. Is equal to what? 0. Because 1 over infinity, so 1 over what? Infinity. 1 over infinity is practically 0. Because if I take 1 over 10,000, 1 over a billion, it's actually what? 0. It's actually what? 0. Okay. Then now we are going to the trig limits. Now we are saying that, so the ninth one, limits as x approaches 0 of sine x over x is equal to 1. limit as x approaches 0 of sine x over x is equal to what? 1. Is equal to 1. Now, for this particular thing, I'm not going to prove it in this particular video, this particular lesson. This is the part 1. This is the part 1. So in the part 2, I'm going to prove why the trig ratios have those what? Values. Have those what? Values. So just subscribe and you'll get the latest video. So why these trig values have this value? So the 10th one, we are saying limit as x approaches 0 of tan x over x is equal to 1. Now the 11th one, we are also seeing limit as x approaches 0 of sine to the power negative 1 of x over x is also equal to 1. It's also equal to 1. Then we're also saying that, so the 12th one, we are saying limit as x approaches 0 of tan inverse of x over x is also equal to 1. Also equal to. Now take note, this x here is measured in radians. This x here is measured in what? Radians. So for the 13th one, so I said follow and subscribe because this is the part 1. The part 2, I'm going to prove why all these are what? So I'm going to what? Prove why all these are so. So we are saying the 13th one, limit as x approaches 0 of sine x degrees over x is equal to pi over 180. It's equal to what? Pi over 180. Now this is basically equal to 1. If you know that pi represents 180, so 180 over 180, which is equal to what? 1. But for this particular one, we are dealing with what? Specifically in what? Radians. Specifically in what? Radians. This particular one, because of the degrees here, we are dealing specifically in what? Radians. Radian what? Measure. So we can't simply just put what? 1 there. We have to put what? The radian measure. So pi over 180, basically 1. But because we are dealing with what? Radian, so you can't actually put it there. Okay. Then from the trig, let's move straight to some exponentials. Somewhat exponentials. So the 14th one, we are saying limit as x approaches 0 of a to the power x minus 1 all over x is equal to log to the base e of a. Is equal to log to the base e of a. Now, once more, for the proof, stay tuned for the part 2, because part 2 I'm going to prove why all these are what. So, now for the 15th one, we are saying limit as x approaches 0 of e to the power x minus 1 all over x is equal to 1. Is equal to what? 1. So as x approaches 0 of e to the power x minus 1 all over x is equal to what? 1. Now you can see this proves it. For this one, you can see directly a is what? E. So from here, for this, the 15th one, a is what? Equal to e. Now log to the base e of e is equal to what? 1. Log to the base e of e is equal to 1. That's why this one is actually equal to what? 1. You don't even prove, you just have to what? Observe. So we are saying that this is what they've given us to look onto. But we decided to bring the a as what? E. So limit as x approaches 0 of e to the power x minus 1 over x is basically equal to what? 1. Where a is equal to e. So we are saying that this is log to the base e of what? E. So we are saying that it's what? Log to the base e of what? E, which is equal to what? 1. Okay, so then for the 16th one, we are saying limit as x approaches 0 of e to the power lambda of x minus 1 all over x is equal to lambda, where this lambda is not equal to what? 0. Where this lambda is not equal to what? 0. Now for the 17th one, this is a special case. Now look at, so we are saying limit as x approaches infinity of a to the power x is equal to, now this is equal to 0 if a ranges in the interval 0 less than or equal to a less than 1. Now if a is 0, if a is what? 0, which means that this will automatically be what? 0. This will automatically be what? 0. So as a approaches what? Values closer to what? 0, it tends to be what? 0. That's what it means. Now it is equal to 1 It is equal to 1 if a is equal to what? 1. Because 1 to an exponent is what? The same 1. 1 to an exponent is still what? 1. So 1 to an exponent of a million is still what? 1. So 1 to an exponent of x will be what? 1. That's why it's what? 1. Now it will be what? Infinity. It will be infinity if a is greater than 1. So we are saying it will be infinity if a is greater than 1. So if a is greater than 1 and x is a large number. So if a is greater than 1 and x is large, then it will be what? Infinity. So you can get 2 to the power what? 50. 3.5 to the power what? 60. This is an extremely what? Large what? Number. That's what's what? At what? Infinity. At what? Infinity. Okay. Then the 18th one. The 18th one. We are looking at, for the 18th one, we are looking at another one from log, another one from logarithm. So we are saying that limit as x approaches 0 of log to the base e of 1 plus x all over x is equal to 1. And as I said, in the next lesson, I'm going to prove all these things. I'm going to prove these things. So stay tuned. So limit as x approaches 0 of log to the base e of 1 plus x all over x is equal to what? 1. Then for the 19th one, we are saying limit as x approaches 0 of log to the base e of x is equal to 1. Is equal to 1. Now you know that log 0 is what? 1, right? That's what it means. So this is practically log to the base e of what? 0, which is equal to what? 1. Which is equal to what? 1. That's what it practically is. That's what it's what practically is. Now we are going to take what? An infinity form here. And what? Infinity was form here. We are going to look at a special case. 1 to what? The power of what? Infinity. 1 to the power of what? Infinity. Now remember 1 to the power of infinity is basically 1, because 1 to every number is 1. 1 to 50,000 is 1. 1 to 60,000 is 1. 1 to a million is still what? So as I said, 1 to an exponent of what? A million is still 1. Now if you can take your calculator and check. If you punch 1 to an exponent of 10 to the power of what? 100, we are going to get a math error. We are going to get a what? Math error. So this particular thing is called a special limit. So we are saying special. A special what? Limit. A special what? Limit. So we are taking it into context. We are taking it into what? Context. Now we want to express a certain limit here. So look at this, what we want to express. Limit as x approaches e of into bracket 1 plus f of x, this to an exponent of 1 over what? G of x. 1 plus f of x, this to an exponent of 1 over what? G of x. Now if x approaches 0, you can see 1 over 0 is what? Infinity. 1 over 0 is what? Infinity. So we will be getting, so if f of x approaches what? So let me write this. So this will not exist. So does not exist if limit as x approaches what? 0 of f of x is equal to limit as x approaches 0 of g of x, which is equal to 0. Now you can see if I put 0 here, I'll come and get 1 plus 0 all to the power what? 1 over 0, which is basically 1 to an exponent of what? Infinity. 1 to an exponent of what? Infinity. 1 to an exponent of infinity. So we are saying it does not exist if limit as x approaches what? 0 of f of x is equal to limit as x approaches 0 of what? G of what? X, which is equal to what? 0. Now there's a what? A solution for this. A solution for what? This. So we are saying the solution for that, so I say stay tuned, because I'm going to prove this. This is very what's important. I'm going to prove this in our next what lesson. So stay tuned. So this has a solution. Has what? A solution. And its solution is e to an exponent of x, e to an exponent of x e to an exponent of limit as x approaches a of f of x over g of what x. Now with Euler's number, we know that if you have e to the power 0 is actually 1, right? Now if you have so e to the power what 0 will be what 1. E to the power 0 will be what 1. So e to an exponent of what 0 is equal to what 1. So we are saying this particular thing does not exist if limit as x approaches a of f of x is equal to limit as x approaches a of g of x, not as x approaches 0. Please make that correction, not as x approaches what 0. So we are saying that this is a solution for it. This is a what solution. So you simply, that's what I said, state, I'm going to what prove this and speak more about this. Very important. There are other what special what limits there, which I'm going to talk about in this part what 2. So now let's move to another thing under the limit. So there's the last thing. We are looking at infinite limits. Infinite limits. So this is what we want to look at. Infinite limits. So we are saying that limit as x approaches a of f of x is equal to infinity. Limit as x approaches a of f of x is equal to what? Infinity. So this is actually made large by taking x sufficiently close to a but not equal to a. So you take x sufficiently close to what? A, but not actually equal to what? A. Now you can make the f of x, the limit as x approaches a of f of x very what? Large, such that it is termed as what? Infinity. It is termed as what? Infinity. It is termed as what? Infinity. So this is the end of our lesson. So stay tuned for the part 2 of this particular lesson. Stay tuned for the part 2 where we'll be proving much of all these particular things. So like, share and subscribe. Like, share and subscribe. So like, share and subscribe to at made easy v3j. So stay tuned for part 2 for the proofs, for asymptotes, for the laws and other theorems. So for the proofs, asymptotes, laws and other theorems. Thank you.